When first introducing resonance, especially in first year, maybe honors or regular chemistry, we go through the idea of, is there just more than one way to draw this that follows the five rules? Really, resonance isn't just saying we can draw it multiple ways, but resonance is about having multiple molecules that are truly equivalent to one another. So when we draw two structures, we have to evaluate, are they really the same thing as one another? And if not, which one is better than the other? In the example of ozone, which we'll scroll up to right here, this and this, those are really the same thing. The double bond and or the extra lone pair is on an oxygen atom in each case, and there's no reason why it would be more likely to be in one place than in the other. That is true resonance. Carbon dioxide is an example where there is multiple ways that you can draw it, but it doesn't exhibit resonance because the other ways to draw it are so much less favorable or less likely that we don't really think that that's a important representation or an equal representation. So CO2, for example, we almost always see drawn like this. It takes a little bit of deeper searching on the internet to find a picture like this, because this one's symmetrical. Everything has its 8. Oxygen has the electrons that it wants, and carbon has the electrons that it wants. Over here, we still have complete octets on every element. We still use the right number of electrons, but the oxygen on the left and the oxygen on the right aren't the same or equal as one another. Down here across the bottom, we have numbers that are called formal charges. Formal charges are a useful way of proving whether something's better or not. Down below, I've got the formal definition and process for how to find a formal charge, but really it's about thinking about how many electrons does something want around it based upon the valence electrons that it brought. So when we have a bond, whether it's a single, a double, or a triple, both elements have access to and are sharing those electrons. That's what's holding the atom together. This nucleus pulls onto those 3, this nucleus pulls on, onto those 6, this nucleus pulls onto those 6, and because they're both holding the same 6 electrons, they are stuck together. But in a sharing situation, like if you're sharing a pizza with your friends, really, yes, both of you have that pizza, but it's as if one of you has these 4 pieces and the other has those 4 pieces. In a bond, carbon and oxygen each have all 4 of those electrons, but it's kind of like these 2 are mostly belonging to carbon and these 2 are mostly belonging to oxygen. That's not true in terms of the way the bond functions or the nuclei, but it does help us understand why something is more favorable than the other or what a formal charge is. Because when I split this bond down the middle, I see that oxygen has 4 of its own electrons, plus we would assign or give it 2 of the electrons from the double bond. The carbon has none of its own, but it's got 2 from this bond and 2 from that bond. Those are important numbers because we know from the periodic table that carbon brought 4 valence electrons, and here it's as if it still has its 4 around it and it's just sharing those. That is a stable arrangement for carbon, so it doesn't have any extra electrons, but it's also not short any electrons. The oxygen brought 6, it has 4 of its own, and then it put 2 of them into the sharing pot. That means that it has 6 around it of its own. It brought and has an equal amount. That's what formal charge is. How many more electrons are next to you than you brought? How many fewer electrons are next to you than you brought? Over here, we've got positive and negative charges because the oxygen's got its 6, plus it's got an extra. So the 6 electrons that it brought, it kept to itself, and it's actually kind of sharing unfairly one of the electrons from another element. Here, this oxygen has only 2 of its own electrons. It's got 3 that it shares, but it brought 6 and now only has 5 around it. So it has fewer electrons than it brought, The oxygen over here has more electrons than it brought. And if we try to balance the electrons with the positive charge or the Zeph, they aren't equal anymore. So formal charge is made up. It's just a way for us to kind of think of, with those sharing electrons, how are they being shared? So these are not real charges. This is not what really happens. Down in this Lewis structure, that carbon has all 6 of these electrons attracted to its nucleus, but for formal charge's sake, we split them in half as if 3 of them belong to the carbon and 3 to the nitrogen. So some of these things here are not actual facts of where the electrons are hanging out, but they are important things that can help us to understand why one drawing may be better than the other, why CO2 has double bonds rather than a single or triple. So the process here is what I described. We look at the number of valence electrons that element brought. We give it half of its bonding electrons. We count for any electrons that belong just to that element. And then we're thinking about the formal charge is how many more electrons or fewer electrons does it have compared to what it brought with it. So a positive formal charge is because an atom has fewer electrons around it than it brought. A negative formal charge is because it's got some extras. HCN right here proves why carbon with its 4 valence electrons wants to form 4 bonds, because in doing so, it's shared exactly 4 electrons. Nitrogen wants 5 electrons around it, which is why this is more likely than that. So this is different than polarity. This is different than shape and hybridization and all of the other stuff that will come after this. This is a made up way of us checking to see, are 2 Lewis structures perfectly equivalent, or is one more favorable than the other? You will have to use this skill to differentiate between better and worse Lewis structures. Sometimes you're given multiple structures, sometimes you have to draw multiple structures, but it is important to recognize, first and foremost, fill your octets. Only if you can fill all of the octets with the right number of electrons is it even worth checking the formal charge. After you have done that, we then use formal charge to see, are 2 resonance structures perfectly equivalent, or is one more favorable than the other?